So what I want to do with this presentation is called Roving the Solar System from Lunokhod to Curiosity and beyond. And before I get into talking specifically about rovers, I thought it might be good to review how we explore the solar system, because if you don't follow NASA's robotic solar system exploration program that closely, you may be confused, because sometimes you hear about orbiters at one planet and landers at another and rovers at another, and you might ask, well, why do we have this strange set of missions out there? But it turns out that there is actually a logic behind the way we explore the solar system. We do what we call a phased approach. We do what's technically possible, what we have the engineering skills to develop and build. We do what's affordable. We want to do the things that we have the money to do, given whatever the budget is at a given time. And we do the easy stuff first, accomplish it successfully, and then we try the more complex things. And in terms of robotic exploration of the solar system, this is the order of the missions that we do. The easiest to do is to do a flyby. Launch a spacecraft, flies by a planetary body, collects data as it goes by. The next hardest thing to do is to send a body, an orbiter, something that will actually go into orbit about a planetary body, and from a given orbit, it has a consistent set of lighting conditions. It can gather your global data set, because you need a global data set of a planetary body to truly characterize what it is. Once you have your global data set from space, you now want to know what's happening on the surface to a much greater degree, and that's where you want to have a lander. And landers come in different types. You can have hard landers. Hard landers are something that you just smack down into the ground, so you collect data as you get closer and closer, but then your lander is broken once you land. So you can't really do the in-depth analysis, so you need something that's soft lands. And a soft lander can use retro rockets or airbags, or now new the Skytrain system, so that your science instruments are intact on the surface and you can collect your data. Now, once you've landed at one spot, then you look around and you realize you want to have information from that rock over there, or that hill over there, or over in that spot there. So you need mobility. And that's where rovers come in. They provide mobility on the land or in the atmosphere. And we'll talk, that's the focus of this talk, to talk about all these different types. The next thing you want to do is you want to bring samples back to Earth, because you can study samples more effectively in our laboratories here on Earth than you can on the instruments on spacecraft. And that includes rock samples, soil samples, air samples, ice samples, whatever. The next hardest thing to do is to send a spacecraft to orbit one of the satellites of the giant outer planets. Jupiter, Saturn, Uranus, and Neptune. They are giant gas bags. They're very massive bodies. They have huge gravity wells. It takes a lot of effort to slow a spacecraft down so it can actually get into orbit of one of those gas giant planets, and from there slow it down even more to get it in orbit of one of its planet-sized moons. Jupiter has 4 of them. Saturn has many of them. And then, of course, the most expensive, the hardest thing to do is to send people and to orbit or land on a planetary body. And thus far, we've only done that for the moon. So here you see the status of solar system exploration as of right now. And across the top, you see these different types of robotic missions leading to human missions. And on this list here, you see the major planetary bodies in the solar system, from Mercury all the way out to Pluto. And for the purpose of this talk, Pluto is still a planet no matter what the IAEA says. And you can see here, we've exposed everything with telescopic observations. We've studied just about everything with flyby except for Pluto. However, we do have a NASA mission called New Horizons that will do a Pluto flyby in July of 2015. Orbiters, we've sent orbiters to all of the inner bodies. We're starting to do the small bodies, asteroids, and comets. The Galileo mission at Jupiter, which I was privileged to work on, the Cassini mission at Saturn. We've sent landers down on Venus, the Moon, Mars, asteroids. We've had an atmospheric probe into Jupiter, and we sent the Huygens probe down on the surface of Titan, the largest moon of the planet Saturn. Rovers, we'll talk about this, the Soviet Lunokhod rovers of the Moon, the Vega balloons in Venus, and the US rovers at Mars. Sample return, we just had robotic sample returned by the Russians. This was their consolation prize for the US beating them to the surface of the Moon in the Apollo program. And we've also had samples returned from comets and asteroids. And then, of course, we've only had humans on the Moon. So the goal of this, of course, is to completely fill in this chart. When we've done that, we will have completely explored the solar system. We can start living Star Trek and go boldly beyond. Okay, so the topic for today is rovers. Why are we interested in rovers? The advantages of roving robotic vehicles is, as I said, mobility. Access to multiple sites or locations on a planetary surface. that allows you to get higher spatial resolution images or higher quality data of the features on the surface. You can also conduct what we call in situ studies, that is direct measurement of the properties of the rock, soil, ice, or atmosphere, their chemical compositions, their physical properties. Now in types of rovers, there's several different types. There's drivers, which have wheels, walkers that have legs, hoppers that jump, floaters, such as balloons, and flyers, such as airplanes, and we'll briefly look at all of those. The ones that we're most familiar, and the one that's actually been deployed for various missions, are the driving rovers. The Lunokhod at the Moon, the Sojourner Mars Pathfinder rover, Spirit and Opportunity, the Athena-class Mars Exploration rovers, and now the Curiosity rover. So the bulk of the talk is going to be about these. Walking rovers, these are something that have not been deployed. They've been tested on Earth. They've been tested on some larger scales, but mostly they've been developed for smaller scales. These are things that walk like insects, although here's an idea for a pressurized capsule walker type rover for the Moon. It sort of looks like the old Imperial walkers from The Empire Strikes Back. But it is something that is being explored, but thus far it has not been deployed. Now here's an interesting type of a rover we call a hopper. This was for a discovery or small robotic mission proposal that was just considered over the last year, a mission called Comet Hopper. This would land on a comet, and then as the comet comes closer to the sun and starts to vaporize, it would use its thrusters to hop to different locations on the comet and thus do analyses in different locations. This mission actually ended up not being selected in favor of another Mars mission, but it's an interesting concept of how you could explore a low-gravity body by hopping. Balloons, this has actually been deployed not by the United States, but the French built balloons for the Soviet Vega missions that went to the planet Venus in the 1980s. And here you see what one of their balloons looks like. These are the concepts for it. And these actually worked, and I'll send a little bit more information like that a little bit later. But balloon missions have also been talked about for other planetary bodies that actually have atmospheres. So here you see a concept for a balloon mission at Mars, and this is one for a balloon mission. This is a lake on Titan, the large moon of the planet Saturn. Those have been considered, but none has been deployed since the initial use by the French and Russians on Venus back in the 1980s. Now, flying rovers, another interesting concept. You see here, this is an unmanned aerial vehicle. We're all familiar with that application for military purposes here on Earth, but it's also possible to do a computer-controlled airplane that could operate on a body that has an atmosphere. And here's a concept for an Ares Mars flight vehicle for the planet Mars. And so this also has not been selected for development, but it has been explored as a possibility. So in terms of planetary rover missions, here are the ones that have been active so far, and this is what we'll talk about in some depth. Luna 17 was the first robotic rover. It was a Soviet mission that went to the Moon, known as Lunokhod 1, the first driving rover back in 1970. As I said, this was sort of their consolation prize for the U.S. winning the space race to the Moon. They did not send people down, but they did have robotically controlled rovers and robotic sample return. They did also try a Mars rover, Mars 3, which I'll talk about a little bit later. It was not successful. Lunokhod 2 operated in the 1970s. We jumped to the 1980s. The Soviet Union had the successful balloons, the Vega 1 and 2 in the mid-1980s to Venus. First balloon mission lasted 46 hours at 54 kilometers altitude. So this particular type of rover was very successful. We skipped to sort of the rebirth of the planetary program in the late 80s, early 90s, and our first successful rover was the Sojourner test rover on the Mars Pathfinder mission that launched in 1996 and successfully operated on Mars. We'll look at that. This rover was a test for the much more sophisticated Mars Exploration rover Spirit and Opportunity, landed on Mars in January 2004, and Spirit ended its operation some time ago. Opportunity is still running. And then, of course, the most recent one, the Curiosity Mars Science Laboratory rover that landed on August 5th. And this is about a future concept that I'll mention at the end of the talk. So, Lunokhod. Lunokhod, it's the, here's a picture of what they look like, these two pictures right here. They remind me of the old Bugs Bunny Roadrunner cartoons where Wile E. Coyote would put like a bathtub on roller skates and all the interesting things That's what it is. But these were solar-powered rovers, direct communication with Earth. The moon is only 3 seconds away at the speed of light, so these rovers were actually operated using telepresence. But you can see here's a sample of the trajectory that they went on versus scale. And here's an example. By telepresence, you actually have a human at a controlled console, and he is controlling a joystick to drive the rover. And just 3 seconds later for the response. So here you see a sample of the wheels on the lunar surface for the Lunokhod, and here's one of their physical probes on the surface. Lunokhod 1, here's the lander where it drove off, a couple of different views of that. Lunokhod 1 operated for 322 Earth days. It traveled 10.4 kilometers on the lunar surface, returned more than 20,000 TV images, performed 25 lunar soil analyses, and it used an X-ray fluorescence spectrometer. That's the device that tells you the elemental abundance of the materials and the elements of the soil. So they did collect quite a bit of good data. Lunokhod 2 operated for about 4 months on the lunar surface. It held the travel record up until recently for the longest distance a rover could travel, 37 kilometers, returned more than 80,000 TV images, panoramas, and did a lot of mechanical tests of the surface. So if you didn't know that there was ever a robotic rover on the moon, there has been. It was a long time ago. It was 1970s by the Soviet Union. And if you are curious about where they are, our current NASA lunar orbiter, called the Lunar Reconnaissance Orbiter, has a very high-resolution camera called LROC, which is operated here at Arizona State University. Professor Mark Robinson is the PI on that camera. And it has been used to photograph all of the equipment from the older missions on it. So Lunokhod's landing sites have been identified in those images. Let me mention about the Soviet Mars 3 lander and rover. This is a conception of what the spacecraft looked like. This top part was the lander, which you see right over here. And then up over here is what the rover would have been. It's one that would have remained attached to the spacecraft with an umbilical and would have used skis to move around. This spacecraft was launched by the Soviet Union on May 28th of 1971. However, when it got to Mars, it ended up landing in a dust storm on December 2nd of 1971. And as you might imagine, Mars with its global dust storms there, that's not a very good thing. An arm would have put the rover on the surface, remained attached to the lander by the umbilical, and used the skis to move around. After landing, communication with the spacecraft lander was lost 14.5 seconds after landing. No usable data was returned, and the rover was not deployed. So the moral of the story is, never try to land on Mars in the middle of a dust storm. So the first successful Mars rover was the 1996 Mars Pathfinder mission. It is the first one that used the airbag landing system. It used that as a test, sort of a proof of concept for Spirit and Opportunity, which would come much later. But here you see the lander station. This is from the mast cam. Here you see the stereo cameras on a mast, and this is the panorama of the landing site. So you see the deflated airbags, the ramps. Here's the Sojourner Rover tucked up against Yogi. They named the rocks after cartoon characters. This is in the Ares Vallis landing site on Mars. And this landing site was chosen because it was thought a catastrophic eruption of water in the ancient past would have delivered a wide variety of different rocks on the surface. You see the Twin Peaks in the distance here, which were actually sculpted in part by water from that flood. This image here is actually from the nav cams that are on the Sojourner Rover looking back at the station, which was named the Carl Sagan Memorial Station. If you can see right here, there's this pole sticking up right here. Here's a closer-up view of this. This is called a windsock experiment. That was built in the basement of the Bateman Physical Sciences F-Wing building on the ASU Tempe campus. My former advisor, supervisor Ron Greeley, expert in aeolian processes, designed this. These cones on the end at several heights above the surface are designed to show you the wind direction and speed for wind at different elevations above the surface. The Sojourner Rover, as you see right here, was very successful. Here's a close-up view of the landing site. There's the Twin Peaks. Here's the wide variety of rocks. And the pattern in which they're laid down is called imbrication, which in geology means they've been deposited in a particular pattern due to the flow of water. Here's the rover analyzing Barnacle Bill. Here it is up against Yogi. It did confirm that there are different rock compositions in this area. And it was a very successful test, and that's what convinced NASA that maybe airbags might be a successful type of landing system to use. So then we jump to 2004 and the Mars Exploration Rover Spirit. It was the first one to land in early January of 2004. It was sent to a place called Gale Crater. It was a giant impact crater. You only see part of it here. That in this crater there's a channel that comes in, and the thought was that water from this channel would have emptied and filled this crater with sediment. So when the spacecraft landed, it started examining the rocks along the floor of this crater and found they were all basalt, which are volcanic rocks, similar to what you see in Hawaii. And it turns out this particular crater was filled with lava flows. So it wasn't until they went to these hills that are called the Columbia Hills after the Columbia astronauts that they actually climb up on top of the hills, and that this rover discovered that these are actually volcano-sedimentary rocks that have been modified by water. So the search for water that this rover was trying to do did accomplish its mission when it got on top here. This shows you the full place where the rover went, up and down the hills, and then exploring this area down here. This is a feature called home plate, and you can probably see all the lines and spots. It spent quite a bit of time around this particular area exploring that. This looks like some sort of ancient volcanic feature. Here's what the rover looks like in 2008. So it's been on there for 4 years, and you can see the dust covering the solar panels. And people often ask me, well, why don't they create something that can wipe the dust off of it? And the answer is that when it comes to NASA missions, the two things that you want to work against are cost and mass. Any type of a device that would have been used to try and wipe off the solar panels would have added mass, which would have increased the cost, which would have mean the mission could not be flown. As it turns out, Mars is windy enough, even in its thin atmosphere, that they had dust cleaning events multiple times for both rovers that would blow the dust off, and then you could start, getting more power again. Now, the Spirit rover became stuck on May 1st, 2009. This was 5 years, 3 months, and 27 days after landing. Remember, these rovers were only designed to operate for 90 sols, 90 days on the Martian surface, and a Martian day is only about 30 minutes longer than an Earth day. So this rover lasted 21.6 times its planned mission duration. The last communication was on March 22nd of 2010. And you can see here, this is a picture of the undercarriage. Here's one of the wheels, and it got stuck in the sediment down there. And so nothing was heard after that. They tried several times, so Spirit was declared dead several months after that. Its odometer, about 7.7 kilometers, about 4.8 miles. So, very successful mission. Its twin, Opportunity, landed on the opposite side of the planet in a place called Meridiani Plana. And you can see sort of this interesting texture on the rocks over here. This particular landing site was chosen because an instrument on the Mars Global Surveyor orbiter that was developed by Professor Phil Christensen at Arizona State University, a thermal emission spectrometer, detected the mineral hematite at this particular location. Hematite is an iron oxide that often, but not always, occurs in the presence of water. So it was thought this would be an ideal place for that rover to explore. The rover landed, if you can't really see, it's a little bit off the screen, in a small crater that had an outcrop right there, and they were able to identify hematite spheroids on the surface, other interesting minerals associated with water at that. And since then, that rock has gone from, or that rover has gone from crater to crater to crater, continuing to explore the materials in this particular landing site, in this particular region here. Right now, it has just entered a crater called Endeavour. It's a very, very large crater, and here you see the rover tracks right over here, and it's been continuing to explore down as time has gone on. This is another close-up view as it's come down inside a broken piece of the crater rim. Opportunity's had a lot of accomplishments over the years, from imaging dust devils to exploring iron meteorites that occur on the surface of Mars. Here's a couple of different panoramas from its camera. This one in particular, this is the most recent one from the most recent wintertime that the rover spent, a place called Greeley Haven, named in honor of my late supervisor at ASU, who was a member of the MER team. So Opportunity is still operating. It's going around inside that crater and continuing to explore the rocks in there all these years after it landed. But now I'd like to go and talk about the new rover, to talk about the Spirit Opportunity rovers to the new Curiosity rover. The science goal of the Curiosity rover, which is called the Mars Science Laboratory mission, is to explore and quantitatively assess a local region on Mars surface as a potential habitat for life, past or present. It wants to assess the biological potential of at least one target environment for the nature and inventory of organic carbon compounds, the chemical building blocks for life, look in the textural features, the microcord evidence of biological activity. Also to characterize the geology of the landing site, the chemical, isotopic, and mineralogic composition of the surface and near-surface materials, the processes that form the rocks and soils, assess the role of habitability, what role did water have at this landing site, the long-term timescale of atmospheric evolution, water, CO2, etc. And to characterize also the spectrum of surface radiation, including galactic cosmic radiation and solar proton events. And the reason why this is important, if we're ever going to send people to the surface of Mars, we need to understand what radiation environment they're going to have to be exposed to. So this is just a list of the instruments on there. There's a wide variety of cameras. There's a wide variety of spectrometers, including that laser ablation mass spectrometer called ChemCam. The radiation detectors. It has a very sophisticated sample analysis suite, which is part of the reason why this rover is so expensive, that allows it to determine the isotopic composition of carbon to help differentiate between carbon that could be produced by bacteria, by biology, versus inorganic processes. So here's a diagram of the rover itself, and if you want to see just how big this is, it's the size of a Mini Cooper. There's a full-size mock-up in our new interdisciplinary science and technology building on the ASU campus. But you can see here the six-wheeled rocker bogie suspension system, the main body of the vehicle right here. The cameras and the laser spectrometer are all on the mast, radiation sensors in the back. Here's the inlet ports for the internal chemistry experiments, and here's the robot arm, and the raw arm has scoops, sieves, brush, the geologist hand lens. It's called Molly. It's basically a geologist hand lens for looking up very close and in color. The elemental abundance device, APXS, and it also has a drill. It can extract a 2-inch, about 4-centimeter drill core of material to deposit inside the rover for it to analyze. Now, just to emphasize what this rover can and cannot do, it is not a life detection mission. It is not designed to detect present-day microbial metabolism. It does not have the ability to image microorganisms or their fossil equivalents. What it can do is it can detect complex organic molecules in rocks and soils. It can identify the isotopic composition of inorganic versus organic carbon. It will search for chemical or textural patterns indicative of biologic versus physical processes. Now, where did we decide to send this particular rover? There was a long period, multiple years, the Mars community assessed a variety of locations on the surface of Mars. And first of all, you do what the engineers tell you can do. There's some places, certain elevations, certain latitudes that are off limits. So you take that out. Then from what's left, are there interesting science targets to accomplish the goals that you want to have? From that, they're able to narrow that down to several different lists, and these were the final 4 candidates for the landing sites. And they're all relatively interesting. These are color-coded DTMs, so blue is low elevation, red is higher elevation. Everswaldy Crater has a river delta in it. Holden Crater, here you see a channel depositing sediment into it. Marth Vallis is an old channel here with a lot of phyllosilicate, clay or water-bearing minerals. And then Gale Crater right here, which has this large sedimentary mound on the surface. So after narrowing it down to these 4, and then taking it to NASA headquarters, it was finally selected that it would go to Gale Crater. So you see this crater, it's about, what, 56 kilometers in diameter or something like that. Here's the landing aeroliths. So the rover should land somewhere in this with all of its technology. And it's very close to the edge of this giant mound called Mount Sharp, which has layer after layer of sedimentary rock, including some of this phyllosilicate clay minerals. So it's an ideal candidate to test to look for all this stuff. So here's what the rover looked like when it was put into its back shell on October 6th of 2011, prior to the November launch. And this does the size comparison. Here's a couple of engineers for scale. Here's the Sojourner Rover. Here's the Spirit and Opportunity rovers. And here's MSL, the Curiosity rover. It just shows you how much bigger this is. This is so big, they could not use the airbag landing system. They also wanted to be very cautious about using a retro rocket lander because they thought that if it landed and there were retro rockets all around, they would scoop up enough dust that would contaminate the science laboratory instruments on the front of the rover. So they had to come up with a totally new way of landing this particular spacecraft, and that's where they came up with the Skytrain landing system. And I'll skip the movie here, but just jump ahead. Since many of you said that you saw the actual landing, just to remind you, here is the various aspects of it. Using the heat shield to slow the spacecraft down, separate, using a supersonic parachute to go subsonic, using very precise landing, separation of the back shell, and then using the Skytrain system. The Skytrain actually slows it down to a point, then lowers it another between 10 and 20 meters down on a tether. The retro rockets are up here, so the idea is that you're going to disturb the soil much less and less chance of it contaminating the instrument. So drop it down and then fly away. And as we all know, it had a perfect landing. So this happened during the Olympics, so that's why I put that in there. So we are also in a very good position. The Mars Reconnaissance Orbiter was orbiting at just the right position that it was actually able to take a picture of the spacecraft, the rover, as it was landing. So here's the parachute, and here's the back shell. So the rover is still tucked in the back shell. You can, in better light, you can actually see the patterns on the deployed parachute up here. So here's a perspective view. This is from the German stereo camera on the European Mars Orbiter Mars Express, another mission which I work on, and showing you the landing air ellipse right here relative to the Gale Crater and Mount Sharp. And here is the flyby after landing to show you all the different parts of the landing system where they ended up being located on the surface. So the Skytrain, after it released the rover, went off and crash landed over here. Parachute and back shell landed here, the heat shield landed here, and Mars MSL is right over there. And here's a color view. If you look really closely on the image, you probably can't see it on the screen. There's a nice dark spot right over here where the rover is. So you see this black stuff over here, that's where there was still enough thrust from the retro rockets to blow the bright dust away. So when you see darker stuff, it's actually the surface. So now I'm going to go through, and the lighting in here is a little bit problematic, but I'll go through sort of a montage of the images and things that have happened since the landing on August 5th. So one of the first images from the navigation camera, so you see the wheel of the rover right over here. You can see part of the rim of Gale Crater over there. Here's the view. Here's two of the wheels. This is underneath the rover bus. Here is the shadow of the rover, and then Mount Sharp actually goes up over here, so you can see the first profile of Mount Sharp over there. Here is a picture that was returned. They had a descent imager, so it was taking pictures as it was descending, and here's the heat shield after it is separated as the rover was landing. Here's the first test image from the hand lens imager on the end of the robot arm, projected against the background here. This is with a dust cover on, that's why it looks pretty hazy. But things match up pretty well. This is while the robot arm was still deployed. So they did their first 360-degree panorama. This is on Wednesday, August 8th. So just over a month ago, they did their first panorama of the landing site, the first color images of the ground were returned right here. And they actually noticed some bedrock was exposed. Even though the thrusters were still very high, they were able to blow dust away from several spots on the surface. And these are ideal candidates for the first study to test some of the instruments. So the first high-resolution 360-degree panorama was returned on August 9th over here. Extended color view of the area. Here's a couple of the spots where the thrusters blew the dust off. Here's more high-res images. This is showing some of the outcrops on the surface. This is a blow-up of this box right over here. This one over here, just showing more views. These are the wheels on the rover right here. Here's from the week of August 13th to 17th, much greater view of the wall of Gale Crater off in the distance. And this is a false color view showing some of the different rocks and the bedding as you go off into the distance. There was a teleconference on August 17th, and here's the first view, complete view of the rover right over here. You notice there's no solar panels on this thing. It's powered by this device here. This is called an RTG, or radioisotope thermoelectric generator. It uses a ceramic form of plutonium that actually decays, and the decay they use to generate heat. This is something that you use in places where you can't use solar energy, or in the case of this rover, this is supposed to be a long-term rover, and so solar panels wouldn't last as long as they want this mission to last, so they use these RTGs to power the rover. These have been used since the 1960s. All of the deep space missions that NASA has sent into the outer solar system use these to power them. And they've been operated very successfully and very safely since the 1960s. Here you see an orbital image, and it shows the base of Mount Sharp over here. Here's the landing site. This is going to be the first target that they're going to get to in a couple weeks to study. And then over the course of the next couple of years, they're going to slowly work their way to the base of Mount Sharp and then up this sequence here to study all of the sedimentary rocks. And here's a really good view, and you can see off in the distance, here's a scale bar for 2 kilometers. But you can see here the layering, some of the rocks in the distance. And here's some darker sand dunes in the foreground. So this is from August 17th. Here's another view of the landing site. They want to go to this site first here because this is the confluence of 3 different geologic terrains. You have to see this one. This one is a little bit different in morphology or shape, and then this brighter terrain here. So this is a good target to see how the differences between those 3 terrains. Here they're giving some names to those scours there. Here's the first rock where they tested the ChemCam, the laser spectrometer. Here's a close-up view of that rock there. Just showing you how that's going to work. So here's, you notice there's a period here. They haven't moved yet. They take a 2-week period to test everything before they try and move. So this is the week of August 20th through 24th, right over here, Panorama. They deploy the arm for the first time to make sure that it works. Here you can see they're testing the wheels, they're rotating them around to make sure that they work before they start driving. And then here was the first drive. This was August 21st. And you see here, it's kind of hard, but there's a spot that were blown away from where it landed, and then you see the tracks driving away, but you don't see anything else. So this tells you this is where it actually landed and where it drove. And here you see from moving around there that they actually successfully could move. So the week of August 20th and 24th, where they did the results of their first chemical analysis of this rock, basically it's volcanic basalt, but it proved that it works. Here's several other interesting rocks there that were nearby that they were going to explore. And week of August 27th through 31st, looking back at the landing site, more images. They're starting to use their color more. And here's a scale of from near to far into the distance. And for example, this peak here, what this says is 10.7 kilometers. It's 16.2 kilometers to the high point over there. So there's a long way to go to get up that sequence. But here's a really great view of the different layered rocks. And the rover over the next 2 years is slowly going to be going and exploring these different layers here. And this is the first week of September. And this shows the traverse that it's made up to that point on its way to this spot over here. These are just some more pictures of the drive and the parachute and backshell from orbit. Here's a good picture of you can actually see the tracks that the rover is making as it's pulling away from its landing site over here. The week of September 10th through 14th, here they're testing, you see these things moving here, they're opening and closing the sample inlet doors to make sure the system is ready to go. And here's a great panoramic view. This is a view of the undercarriage of the rover, and you can see all 6 of the wheels right over here. Here's a view after day 43 or Sol 43 as it continues to move. Another interesting rock that it's going to be looking at. This was from a press conference that was on September 27th, and this is, I think, the most recent information I had. And the interesting thing is, looking at this rocks, they see this is very similar to a terrestrial conglomerate, a rock that was transported by some form of debris flow. And they noticed that there's at least some semi-rounded to rounded pebbles in with this stuff here. So the suggestion at this press conference was that this might have been an area where you had water transport this material in say a stream bed type of path. Alternatively, it could be some sort of a gravity or impact driven base surge deposit. But all of these opportunities are different hypotheses are going to be explored, and if it's true what they think, that water was involved in this, that's a very good sign that they landed in the right spot. So that's where we're at right now. There's a press conference that was at 11 o'clock, which of course I couldn't hear because I was sitting over here, but we'll see how the rover goes. So I need to move my marker a little bit because we're now in over here, so operations are now underway for this rover. Now, what about the future? What are we going to do now? Well, of course, everybody's going to be interested in Curiosity because it's going to be working for, a couple of years now. But now that we've proven this Skytrain technology, are we going to use it further? Well, there was a plan in place for further exploration. NASA and the European Space Agency were going to work together on a mission they call ExoMars, and here's a version of their early rover. And they were going to work with NASA on a rover to basically start the first part of a Mars sample return campaign. That would involve 3 separate missions. A rover to drill and store samples for retrieval, another mission that would have sent a Mars ascent vehicle, basically take the samples from the surface of Mars, put it into a rocket and launch it from the surface of Mars into space, and then the third part would have been an Earth return vehicle that would have picked up that sample from a near Mars environment and returned it to Earth. Where it would land on the surface of the Earth, similar to what we've done for the other sample return missions. This time frame would have been like over 10 years and would have cost about $8.5 billion, which is why it would have had to be international, so that multiple nations could share the cost. However, given the current NASA budget environment, the current presidential administration decided not to pursue this, and we broke our agreement with the Russians, or with the Europeans. They're not going to try and do this project with the Russians. And they asked NASA to conduct a program review about how we can move forward with Mars exploration with a tighter budget. And they just delivered their report on September 25th. And this graph here shows you various concepts for orbiters and for several different types of landers and their costs. So it is possible to do aspects of that sample return for much less, but you're still talking in the hundreds of millions to over $1 billion price range, depending on how you look at it. So it would be a shame not to use the Skytrain, I think, now that it's proven successful. But you all know the nature of our current economic conditions. We're in the middle of a presidential election. Who's going to get elected? That could change the direction on how we do things. So we'll just have to wait and see what happens like that. Here's an artist's concept of a landed spacecraft with a Mars ascent vehicle, a rover that had delivered some samples on it. So Mars sample return is the highest priority for the scientific community for Mars exploration for the next decade. So we will see if that in some form can come to fruition. Okay, let me summarize this presentation for you. Robotic rovers are used for multi-site, mobile, in-situ analyses of planetary surfaces and atmospheres. They've been successfully used on the Moon, they've been successfully used on Venus in the form of balloons, and we've had them successfully used on Mars. The Curiosity rover is the next major leap in planetary roving. It is a nuclear-powered, long-distance, designed to go at least 20 kilometers, mobile geochemistry and mineralogy laboratory. It was a very expensive mission. The total mission lifetime cost will be about $2.5 billion. But if the landing is any sign, this should be a very, very important mission with a successful Skytrain landing system. Could usher in a whole new era for robotic roving if we decide to make that choice. Aerial and surface rovers are being designed for many solar system targets, and I predict rovers will be a necessary part of any Mars sample return campaign to identify and cache the samples on the Earth. So that's the last slide I have, and I'd be happy to take questions from any of you. Thank you very much. Yeah, hold up your hand. Yes, sir.
I see the cost associated with sending something up to hundreds of millions to billions. What's the majority of that cost? Is it actually sending it? Is it development? What's a large chunk of that?
Most of the cost is in the actual engineering and development, the actual design and then the bending of metal and producing it, because you're paying all these engineers to build this thing. Once the spacecraft is launched, it's operations cost and paying the people to control it and the scientists to analyze the data. That's a much smaller fraction of the total cost there. So mostly it is in the actual design, building, and construction of those things. And remember, we've picked all the low-hanging fruit. We've done all the flybys, we've done almost all the orbiters, so now we're into the more technically challenging, more expensive things. So that's why the robotic costs for landing systems and rovers in particular are so much more expensive. Other questions? Yeah.
Is there an ability to determine the origin of organic material or compound should they find it, as far as, like, is it sourced on Mars, or is it like from ejecta from like an impact event on Earth? And
I would say that robotically that capability does not exist. That's why you need a sample return mission. You need, once you identify potential samples, you need to bring those back to Earth, because you need Earth laboratories with the more sophisticated equipment and the hands-on of scientists to look at this stuff to actually make a determination about whether organic material, if it's found, is of a terrestrial origin that's just been deposited on Mars by an impact event, whether it's vice versa, or whether something is transferred. But material goes all over the solar system. You know, the gravitational effect of Jupiter causes material to hit the inner solar system and impact. It's redistributed icy material throughout the solar system. The giant planets, a theory says, move from their original locations into their current configuration, and anytime something like that moves, it disrupts all the smaller bodies and causes major impact events. So things have gone all over the place, and it's going to be a great challenge if we do get samples back from Mars to make sure that they actually, if they have life or few life materials, whether that originated on Mars or whether that came from someplace else.
About how much it costs the mission is the stuff that just gets used up in getting there, like the rocket and
the rocket is the launch vehicle is usually just a couple $100 million. So it's a very small part of that. The vast majority of the cost is in the actual design and building of it. Yeah, I don't know if you're looking for a percentage for a number. I don't know if I have a good one off the top of my head, but I would think at least 50 to 60% is in that. Other questions? Yeah.
So this latest lander, what's the most exciting piece of data for you that's brought back?
Well, that's very interesting, that picture right there. This occurred while I was on travel. I just came back from Europe for another planetary mission meeting here. I was talking with one of our faculty at ASU, a geology professor, and said, no, they've got it all wrong. You don't need water to produce things like that. So it's going to be a very interesting debate. But I think the most exciting thing for the Curiosity rover mission would probably be a successful landing. Because a lot of us in our community were just not convinced that Skytrain is like a Rube Goldberg thing. All these things had to happen correctly and happen in the right order, or it would have been, you know, a multi-billion-dollar pile of mess on the surface. But it did operate and land successfully. So that's probably the biggest thing. And the fact that all of the instruments seem to be working just properly. There's nothing wrong or broken of any consequence on the rover. So, you know, it's a fully operational device, and, you know, it's going to be, the science team on that's going to be having fun for a couple of years. So I think that's what's most significant.
The Skytrain, I mean, how well did it work? I mean, perfectly, or what sorts of issues came up with it that you...
Based on what I heard listening to the press conferences, and I'm not a member of the Curiosity team, so I don't know what they talk about internally, but just by what they said, it was basically flawless. So
did the theory about not disturbing too much of the ground, did that pan out? Or?
It panned out apparently well enough. I guess I should say, now that you mentioned that was a bit of a surprise, because if you look on some of the pictures of the rover deck, there is some small particles on that. So even when it lowered it on the Skytrain, there was still enough disturbance from the thrusters that some small material got on top of the rover deck. But since those caps were on the sample inlet things, there was no contamination. Because they're testing that now, and there's no evidence of that. So it worked well enough for that, and now we have the ability to basically deliver 1 ton of robotic equipment on the surface of Mars. So that's a great capability to have.
I was wondering, why did they wait 2 weeks to make sure the equipment's running? How could they fix it?
Well, basically they have this period between 2 weeks to 1 month of test out. They basically do one thing at a time to make sure it works. But you know, they didn't just wait until 2 weeks to start driving. They wanted to make sure everything was working properly. And remember, you have this time delay between Earth and Mars, and even though they have people working on Mars time, so That means that the scientists at the Jet Propulsion Lab, who are there during the first 90 days of the mission, they get up when it's sunrise at this landing site on Mars and they go to bed. And that changes 30 minutes each day. So it's like being in a state of perpetual jet lag because your day starts 30 minutes later every day. So that affects how well you can operate. But they just did a phased examination of each piece of equipment on there, and once they verify that it worked, then they can drive. Now, you ask, how do they fix things that are broken? It depends on what the nature of the thing is. If it's a software problem, you write new software and upload it to the spacecraft. If it's a piece of equipment, it depends on whether they have redundancy. Most engineers design planetary equipment so that it has some form of redundancy. So there's a backup computer for the main computer. There's a backup transmitter for the main transmitter. Now, if one of the axles and wheels was broken, that would be a problem. However, the rover has 6 wheels, so it can drive even if one of the wheels is broken. Spirit and Opportunity did that in their later years. But yeah, depending on what the nature of the problem is, there could be some things that could be broken that could not be fixed, and then you have to work around. And that's where the engineers earn their pay, trying to see how you can accomplish the mission when a major thing is broken. On the Galileo mission to Jupiter, the NASA Jupiter orbiter, the high gain antenna was an umbrella type antenna, and it failed to open. So we lost our ability to transmit lots and lots of data through the high gain antenna, so they had to redesign the mission to use the low gain antenna and develop data compression techniques that allowed us to transmit more images back through the low gain antenna. And that's what salvaged that particular mission. Other questions? Yeah?
One thing that did fail was one of the weight sensors.
That's right, yeah. That was mentioned as a failure, but that's not a consequence for accomplishing the major objectives. What they call the level 1 science objectives. Those are the things that must be accomplished in order to justify the expense made for the mission to be worthwhile, and that didn't compromise that.
Yeah, and they have a redundant one as well.
Mm-hmm. Mm-hmm.
How much autonomous programming does it have, or do they have to give it specific instructions every day to do exactly what they need to do?
They basically do it that way. They look at where it's at the moment. They pick whatever target they want to do. Then they upload commands to the spacecraft for it to drive from A to B. Then the next day they evaluate it and do it again. Now the rover does have some onboard software so that if it's driving and there's a rock over there that is, depending on what size it is, it can analyze it and decide, does it want to try and go over it or does it want to go around it? So yeah, there is some of that autonomous software there. That's been growing more and more over the last decade as NASA's been exploring that kind of capability. So this has more than any other mission. But still, in terms of what it's going to do, it's still scientists looking at data on a given day, deciding what to do, uploading the commands to the spacecraft, the rover, for it to do it, and then do that day by day by day.
And just a follow-up to that, how much of the time is already taken up, or can scientists, as data come in, make requests that I want to go here and spend a day doing this?
Well, there's a designated science team, and that science team is made up of geologists and atmospheric people and geochemists, and they, as a group, make a decision about where they want to go next, what rocks they want to analyze, what soil samples, what tests they want to do. So they make that decision, and then they go step by step through it. There's sort of a general plan to get to Mount Sharp by this time, but they're just not going to go straight there. They want to see the lay of the land around them. They want to understand what it's made out of, the stuff here, so they have something to compare when they get over there. So they just do it in a step-by-step basis like that. Other questions? Yeah?
How much of the mission is privately funded?
How much of the mission is privately funded? To the best of my knowledge, none of it is privately funded. It's all funded by federal money, by NASA. So NASA has a science mission directorate, and that science mission directorate has 4 divisions: astrophysics, planetary science, heliophysics, which studies the sun, and earth science. And the planetary science division's budget has been about $1.5 billion. NASA's whole budget, if you didn't know that, is 0.6% of the federal budget. That does everything, including the space station. It did the shuttles. It helps contribute to the commercial sector who are developing the rockets to replace the space shuttle, everything. And the planetary science, so all the robotic missions just come out of $1.5 billion, plus the money that funds the scientists to do that. The international partners have instruments, and their governments contribute that. But that has come, once again, from government funding from other countries, not from any private funding. Other questions? Yeah?
What's the lifespan of the RTG?
The lifespan of an RTG is between 15 and 20 years. So that's not the limiting factor usually. But it does go down as the radioactive stuff decays, the amount of heat it's able to generate, and thus electricity it's going to be able to generate decays. There's still enough on the Voyager spacecraft, which were launched in 1977, and we're still detecting signals from Voyagers 1 and 2, which are right now at the edge of the solar system. Other questions? The sheet that I passed out here, this is my mission guide to solar system exploration. The front page lists all of the current and upcoming robotic planetary missions and includes their website. So if you want to catch more information on your computers at home or here, you're free to do so. A really good place to download images from all of NASA's missions is the NASA Planetary Photojournal, photojournal.jpl.nasa.gov, which is why I included it on the bottom of this handout. On the back of it lists the, quote, NASA Year of the Solar System. It's a 1 Mars year, 2 Earth year time period when we had a lot of specific spacecraft exploration events on here. And the culmination of that has been the landing of the Curiosity rover and the departure of NASA's Dawn mission from the asteroid Vesta on its way to the asteroid Sirius, another mission I work on myself. So that's a good resource for you. And there's more copies around somewhere if you want to take it for a teacher or somebody. Any other questions or anything? Yeah?
In the beginning, you laid out the steps of flyby and then orbiting, etc.
Mm-hmm.
Given that we're just now sending New Horizons to see Pluto in 2015, how long do you think it will be until we take the next step or you finish all the steps and actually land something or someone?
Wow, that's a good question. Yeah, it's taken us all this long. Planetary exploration is basically 50 years old. It was the Mariner 2 spacecraft launched by NASA in August of 1962 that did the first Venus flyby. So it took 50 years to get a spacecraft to Pluto. Now, part of it's going to depend on what they discover, what we discover when it does the flyby. Is there something remarkable there that's going to justify sending another mission back really quickly? I think we have, what we have produced is basically a National Academy of Sciences Planetary Science Decadal Survey. It's a 10-year plan of how we're going to conduct solar system exploration. And it just came out in 2011 for this next 10-year period. And it lists what are the major targets we would like to visit, the types of missions we'd like to do. In terms of the big flagship class missions, Mars sample return, and a Europa orbiter. Europa is the icy moon of the planet Jupiter that has the liquid water ocean underneath its icy crust. Those are the 2 top missions for flagship, assuming that there's any money to do stuff like that. For medium-sized missions, there's a list of potential things that range from a lunar sample return from the big South Pole Lake Basin to a comet surface sample return mission to some sort of a Venus atmospheric in situ mission to an orbiter for Jupiter's volcanic moon Io. So there's all sorts of things that are going to be competing. It's a competition for who can write the best proposal, who can develop the mission for the lowest cost. So that plan is what we're going to do. Right now, we want to concentrate on what we discover from New Horizons to Pluto, and then that would feed into any future discoveries for the next decadal survey. So the short answer to your question is, when are we going to send the next thing to Pluto? Anybody knows? Mm-hmm?
All right. Assuming someone didn't care about budget, a government agency, private sector doesn't have budget. Does the technology currently exist, and if not, how long do you think it will take before it does exist, for a manned mission to Mars?
Does the technology exist now for a manned mission? Then you would have some debate on that. Some people think we could do it. I think we need to do a little more research before we're ready to do that. The current plan in the President's budget is to be able to send people to Mars in the 2030s. So the NASA is theoretically developing an Orion crew capsule and a space launch system that is going to be designed to take humans on the next step of deep space exploration, whether it's the moon, whether it's near-Earth asteroids, but eventually onto Mars. And that's supposed to be ready to go there in the 2030s. That's why NASA's been concentrating on letting the commercial sector develop the space vehicles to do the routine supply of the International Space Station with our international partners. So, does the technology exist? In some parts of it do. There's some things that we need to do. It certainly could be developed within 10 years, I think. So I think if the will and the money is there, we could get to Mars with humans in another 15 to 20 years.
Actually, I have a question because I know manned costs are enormous and they take away from these robotic missions. What's the status of the James Webb? Is the Orion taken away from that, or is the Webb still alive?
NASA has 3 priorities right now. One of them is to continue operating the International Space Station through 2020. Another one is to continue development of the Orion crew capsule and the space launch system for human deep space exploration. The third priority is the completion of the James Webb Space Telescope, which is going to replace the Hubble Space Telescope, which is now scheduled to launch in 2018. The James Webb Space Telescope is a very sophisticated robotic spacecraft. It's in the astrophysics division rather than planetary, so I don't know as much about it, since it's not really going to be used for planetary studies. But it's had extensive cost overruns, and that has, taken a lot of the NASA Science Division budget away from other things. But it is the plan that mission is going to go and is going to launch.
I noticed a little gap there for asteroids with rovers. Do you think that will ever happen? Is there anything that Dawn is telling us that is anywhere?
Well, since I work on the Dawn mission, I know quite a bit about that. We just finished a year-long exploration of the asteroid Vesta, the second largest asteroid in the main belt, and we departed and we're on our way to Ceres, the largest asteroid in the main belt. There is a mission that's already been approved called OSIRIS-REx, which is going to be operated and built by the University of Arizona in Tucson, and Arizona State University is going to contribute a thermal imaging instrument. That mission is basically going to go to a near-Earth primitive asteroid, orbit, dock, grab a sample, and return the sample to Earth around 2020, 2022. So that mission is going to be approved. And let's see, I guess I should probably put, that mission's not really going to be a rover, but it will be a sample return. Hayabusa was a Japanese mission that visited a very small asteroid, and it did return some very, very small particles of the asteroid, but not a huge sample as were returned from the other sample return missions. So whether we send a rover proper to an asteroid is going to depend on whether we discover something of significance. Now there is a consortium of companies that is trying to establish the mechanisms to do asteroid mining to help develop a space-based infrastructure. That'll probably take at least 10 years to get going there, but if they discover something, that would be motivation to do something like a rover on that. Eventually you're going to need that to utilize space resources to develop a human-based spacefaring civilization, which is the goal of many people who are space advocates. Any other final questions? Okay.
Dave, thank you so much for...
Yeah, my pleasure.